Thank you for joining my session here. I'm Karsten Thoms from itemis, and I'm one of the developers behind the Xtext framework. Today I want to speak about how to build expression languages in Xtext. And actually, most of the DSLs that I develop with my customers with Xtext, they don't use expressions. Many DSLs are just structural DSLs that describe forms, that describe domain models, they describe state machines, they describe something else. Many things are really structural things. And when it comes to expressions, then people need to know some advanced concepts behind writing grammars with Xtext. And today I want to show you these patterns behind this. Expressions, you know, that's our additive expressions, plus, minus, multiplicative expressions, and so Boolean expressions, equal, and or, and unary expressions, not, and so, and these are the kind of expressions that you may want to use in your language. And there are some challenges that we have to solve there. There's this recursion. Rules may be recursive. You can say plus, 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 minus, minus, something like this. And of course, operator precedence. Some rules have higher precedence than the others. You need to solve associativity in your rules. So if you make brackets, what is related, what is evaluated before the other thing. And of course, ambiguities, that's a very important thing. Your grammar will fast become ambiguous, and that's quite challenging to solve. And if we talk about expressions, we also have to talk about typing. So are the expressions that are related here compatible to each other? And you may know that you can already use an existing expression language when you work with Xtext, that's Xbase. Xbase is already a full expression language which is shipped with Xtext, and that's also the first choice that I would do if I would need expressions in my language. Xbase is used by several languages that we built, like extend. When you work with Xtext, you know extend. And basically, extend is not much more on top of an Xbase. Everything which, all the expressions behind that, that's Xbase. Extend only adds the notion of classes and template expressions, and so it's just a small layer on top of that. And so if you know how well extend works, then this you can already get for free from Xtext. You have tight integration with Java, so you can use Java types. You can invoke Java methods from your expressions. That's quite nice. But what is if you can't use Xbase? Reasons could be, for example, that you want to build a language which is independent from Java. So you want to have a language which integrates JavaScript, or will be rolled out with a pure C++ development environment. These are also the kind of languages that we built. And of course, then JDT is a no-go. And you can't use any dependency on JDT. So this prevents using Xbase. Also, you should be aware that using Xbase is sometimes also downgrading your performance, depending on what you're doing. And you should be aware of that. If you just want to do some basic expressions, some default expressions maybe to initialize variables, that's a typical thing that you want to see. Okay, this variable has a value of string plus something. Easy things. You could use Xbase for that, but it's bringing much complexity into your actual language. And so then you could have the use case that you have to build your own language in Xtext. So, but we can learn a lot from Xbase. But if you look at Xbase, it looks complicated. But actually, the important things aren't, and that's what I want to show you today. So, I want to show you the patterns that you find in the Xbase grammar, which make up the expression language. The Xbase grammar is quite huge and quite complex, and if you don't know the advanced concepts, it just is overwhelming. But yeah, let's have a look how Xbase is created. First of all, quite typical is that you don't generate a meta model. You know that Xtext is quite easy, that you write a grammar and let your meta model derived from the grammar. And usually if you embed expression languages, you won't do that. You would build your own meta model manually and integrate this. This is a small change. Instead of saying generate me a meta model, you're importing an existing one. So that's that way. So that way you have more control over the structures of your expressions, so that you can say, okay, this is an expression, I have binary expressions, I have ternary expressions, and so, something like this. And Xtext yeah, is a little bit nasty when it derives such meta models from your grammar. You would do many things just to tweak Xtext to do it the right way, like you would like to do this. Just don't do that. You can start by creating, by letting your meta model generate it, and then take it as it is, take it under manual control, modify it, and import it. So when you look at the Xbase grammar, the first thing that we see is every rule returns expression. So we have the same base rule that is returned. So any expression is returning X expression. So you would have a concept like expression, X expression, base expression, whatever you call it. So this is the base class of your expression in your meta model. Next thing is each rule will call the next rule at first with the next higher precedence. So this is the first pattern that you can see. Okay, the expression calls assignment, assignment calls or calls and so here you can see the precedence of the rules. I will go a little bit more into detail why this is done, but now just take this pattern. Next thing that we see in the rules is we have this followed by an optional part. It's always optional, either single-valued or multi-valued, introduced by a syntactic predicate. Ever used a syntactic predicate? Who? Oh, not much. Okay, so good to have you here. I will go into this also in a second. And next thing is followed by an assigned rule. Did you ever see this kind of construct in a language for something is assigned to a current? Seen that? Know what this means? No. Okay. So that's because why we're talking about that. And then we have usually operators, and it's a good way to say, okay, they can be extensible and it's better readable if we just make a single external rule that just enlists the kind of operators. You could embed this, of course, at this place. You can also say, okay, this is just equals. But this way it's also a little bit more readable what are the actual operators. And regarding to Xbase, it is also important to do it that way because Xbase is meant to be extensible and you could override this rule. If you embed a language, if you create a language with Xbase, you can say, okay, the assignment operator is not equals, maybe it's colon equals, like in some languages. And then you just override this rule. For your language, this may not be necessary because you would have a final language. We will have rules to express literals. Somewhere you will have something like a Boolean literal, collection literal, string literals, and all those things. They need also to be expressed. What is a bool? Is it true? Is it false? Or what are the expression of that? Here we have in Xbase we have also null literals. Number literals is quite common. So you will, for all your primitive types, you will have a literal expression. And they are collected in one rule. So every literal is collected in a literal rule. Now let's have a look at how expressions are parsed. Let's take this simple example. So we have an expression 2 plus 3. And we want to make a grammar out of that. First thing that we could do is say, okay, we have here a number, and a plus sign in between. So we say, yeah, here's an expression, there's an expression, and a plus in between. So we could come to such a rule. Expression is constructed of expression plus expression, or just an expression. What does this imply? Let's think like the parser. Here we have a left recursion in this grammar. So left recursion is when the first rule in your parser rule is non-terminal and calling itself. And maybe you already faced this. If you wrote an Xtext grammar, it won't be translatable because we use under the hood Antler, and Antler does not support left recursion. This has to be avoided by left factoring. So let's look at this example, how we could parse a sum. We have sum is constructed of 2 parts. It's a binary expression. On the left side, a number, and on the right side, a sum, because you could again make sums of sums. If we feed our parser with just the number literal, what happens? First of all, it starts with the first rule. It will face, okay, here's sum. It will create a sum object. Next, it will face the literal. It will create a number object. And then do the assignment here. So that's the parse tree for this literal. Why do I have a sum here? I only want that this should be the integer. Let's take it one step further. We do this with the same rules. What happens? First, same again. We enter the sum rule. We create a sum. We face the 2, so it creates a 2 number object and assigns this to the left feature. So now we see that plus sign, and it knows, oh, I have to create another sum. I face the 3, create a 3, assign the 3 to the left feature, and then assign the right side of the first sum to the new sum. That's horrible. Now let's do it better. And this is why where assigned actions come into play. Sorry. Okay. This is how it should be. And here we see this assigned action. What does this mean? This here means, you see this is optional here, this part. The whole part is optional. So we will start with an addition, but we'll immediately enter the number rule. And maybe nothing else happens. So if we enter 1, we just have, oh sorry, there's a problem in animation. We will just have a number instance. No addition object involved. And if we do this, what happens? First of all, we face the 2. It will be the number instance. And then we face the plus sign. And now this here comes into play. This here means when you face now the plus sign, then create a sum object. This is introduced by these curly brackets. So this here will create a sum object and assign the current passed element, which was the 2, to the left feature of the sum. That is what assigned actions work. So we assign now the 2 to the left side of the sum, then pass the 3, create a number instance, and assign the right side of the sum. And that's the pass tree that we need. So here you have the necessity to use create actions. Now let's take it one step further. Yeah, you don't only have sums, but we have different kind of operators. So what do we have to solve? Precedence. So we have to say, okay, an addition is less value than a multiplication, and at the end we have a literal, or in other words, we have rules of any kind of priority chaining each other until we find an atomic. That's the rule with the highest precedence. In terms of the rules, the pattern is always the same. We call from the first rule, the second rule first, and the rest is optional. It's always the same. Until we face an atomic. That's the leaf. And now we come to the syntactic predicates. That's this arrow sign. What does this mean? A syntactic predicate basically means it's a hint for the parser. It says, try to parse this pattern. And if this pattern can be parsed, then apply this rule. So it's like a for looking there. If you see these tokens that I'm saying here in my rules, then you can follow this path. That's important to resolve ambiguities, because you can have several rules which look like the same, but a plus could be in some case have different meaning than in another case, and then you have to say, okay, it's not only the plus, there are certain other parts that you have to consider. And if you can match this, then that's path. A popular example where we have to use this is the dangling else problem. This is the same text here, but to which if condition does the else belong? Just the same text. The parser doesn't know that. And this you have to solve with a syntactic predicate. So in this case, you're saying, okay, we're parsing the if part, and when we parse else, then assign the else part to the current object. So you can solve these kinds of problems. Let's have a deeper look. This is then the parse tree that is constructed. The else is assigned to the second if in this case. Okay, that's basically the patterns behind building expression languages. Just yeah, have certain rules after each other with ascending precedence. Then have the syntactic predicates to give the parser the hint. If you can parse this, then follow my path, and it's optional because it could be just the end of the parse tree. That's a basic pattern. Now let's talk about type systems. If you have expression pass tree, then you will have something like numbers, strings, and so. And usually you want to do computations and say, okay, this is compatible to each other. What do you have to implement them? So let's talk about how to implement a type system. It's basically not the problem. You have to answer 3 questions. First, what is the type of an expression? What is the actual type of an expression? Second is, what is the expected type of that expression? And the third question is, are they compatible? And this is actually what you need to implement in a type system. To express this in code, in pseudocode, it could look like this. You have one method that gets an expression and says, okay, what's the actual type of that? Then the same, what's the expected type of that? And then a third method, do they comply? To make it very simple. And this you can check with a type validation rule. Actually, this is a good pattern, but it's nothing that you get in Xtext out of the box. So for your own expression languages, you have to rebuild something like this. A validation rule could look like this. It's actually not a big problem. You have a validator. You will write a validator class. Then you will have something like a type computer, which gives you the types. And then you ask to check an expression. Give me the actual type of the expression. Give me the expected type of the expression. Can they be computed? For some shortcuts, maybe you can say, okay, I can't compute this for that kind of expression. But if you are able to compute both the actual and the expected type of the expression, then you can check, are they compliant? And if they are not compliant, you raise an error. That's actually what's behind validation.
The actual type is the right-hand side, expected is the left-hand side, right?
No. I will explain this now in detail. But good question, Andreas. Just a small hint. Of course, you could add this rule to your existing Java validator. I wanted just to show the way if you want to write an additional class just for type validation, then you have to do some magic. You have this class and you have to add an eager singleton binding to your runtime module. It's the same pattern if you want to decompose validation rules in different classes. Then you will add eager single bindings for each validation class. That's the way how Xtext will pick up this class and execute validations. So when your validation class becomes too big. Just a small side hint. Okay, now coming to Andreas' problem. What is actually actual type? What is expected type? Let's take this. We have a number and a string, and we have an assignment with a plus operation. This here is a number. That's the actual type of X. The actual type of that here is string. You will have some internal type system. For each type that you know, you will build some class and or an enum or whatever. Somehow something that you can say this is a string, this is an integer. This here is also a string because the left side is actually referring to a variable. These are the actual types. And also the actual type of this operation is string because we have on the left side we have a string, and we can say when on the left side of a binary operation, of a plus operation is a string, then the overall expression will be a string. So this is what your type computer has to implement. Now getting to the expected type. Easy first. The expected type of that expression is string because the left-hand side of the assignment is a string. That's the expected type. Okay, this was easy for strings. Now let's take a different example. What's here? We have this here will be actually a number. X is a number, 1 is a number, the result will be actually a number. But the expected type of that expression is actually string. So that's the difference between actual type and expected type. The expected type is depending on the context. The actual type is not. For expected type, you have to consider, where am I? Is it a variable initialization? Then the expected type is the type of the variable. Or is it an assignment? Then right side is expected to be the type of the left side. Or for if conditions, yeah, the expected type is just Boolean, true or false. So that's what your type system has to do. To give you an imagination how this could look like, just an excerpt from existing code for a language which has a rather simple type system. We have a type computer which implements all 3 interfaces. We split it all 3 questions in 3 different functional interfaces. So what is the actual type, what's the expected type, what is, which types are compatible to each other. 3 different functional interfaces, and our type computer just implements all of them. So we're getting some object in, and we can compute what is actually type for an object. For expressions like relational expressions, Boolean expressions, easy, that's just the bool type. That's the actual type of that expression. Sometimes it's recursive, so you have for other kind of expressions you have to compute the actual type recursive. And at the end you just have to answer, yeah, what is the type. This in this type system there's also an any type because some expressions are not declared in this language. This is a special language. So we have an any type, and you can say, okay. If you have some thing like string or integer, it can be assigned to an any type, like object. And for the conformance part, that's also quite easy. Yeah, you look if they actually match. In this case, we have we are able to assign integers or floats to bools. That's the special thing of that type system. So if there is a 1, then it's equal to a Boolean true, or 0 Boolean false. That's so the actual type. So an integer type in this language is assignable to a Boolean. They're compliant to each other. So that's the barefoot way to do this. I want to make you aware of a new project proposal at Eclipse. That's X semantics. It's actually originating from a SourceForge project from Lorenzo Bettini, and he wrote a framework to describe type systems. So if you have a more complex type system, then it will be worth to look at his work and try to integrate that into your language. Lorenzo is also running around here at EclipseCon. If you want to talk with him about X semantics and you don't know how to find him, just come to our booth and we will find him for you and connect you to each other. And last thing, most important thing when writing expression languages and type system, do test first. You have to write tests up front for each and everything that you're doing. Because with every change of your grammar and every change of the type system, everything can be broken. But if you start up building assumptions from the very beginning, then you will recognize if you break something. So that's the very important thing to do. Okay, I'm almost through with my time. So, any questions now? Okay, yeah.
Question
yep.
Related to X-semantics.
I can't tell you much about that, I have to say.
Okay.
Never used it so far.
Because I haven't clearly understood the perimeter and what it does exactly.
You can describe rules about types in a DSL, which is implemented again with Xtext. So you describe which types you know, what are the rules that have to apply to the types, and such things. You can do that. But I have to say, please talk with Lorenzo. It's not my topic.
Because in fact, it's related to another question I had in mind, which is what you have introduced here is something with a use case. I think everybody has when using Xtext, making sum, minus, multiply, divide, and so on.
Exactly.
And most of the time, I have the impression I have written this kind of code, so I have suffered a lot writing this kind of code, and I have seen that I'm not the only one at all to have suffered writing this kind of code. And most of the time, in fact, people are doing quite the same thing with the rule you introduced.
Yes.
And is there another way of, and maybe it's X-semantics, which provides this high-level way of having something such as common rules, kind of everyone uses, to be able to and just to say, okay, on this common base of rules.
A common expression language with a common type system.
Yes.
That's Xbase.
Yes. Yes.
That's also the reason why we implemented Xbase, but as said, it's strongly bound to Java, and if you don't use Java, then you have to build your own from scratch. We don't have such another alternative Xbase. Andreas?
Another related question to him. So we showed already how to provide or implement type checks. But are there any plans in the Xtext itself to provide a facility for type checking? Because there was sometimes from the beginnings Xtext type system, which is now obsolete. And then there is this X-semantics, but it would be good to have such kind of functionality in the framework itself.
Right, would be much work, and I think this is also the answer why we don't have plans about that at the moment. It's not pressuring ourselves in our daily work, so unless someone invests into that and say, okay, I want you to build that thing, I don't think that we will put this on the roadmap. Because yeah, you can just follow the patterns, and yeah, all the languages look more or less the same, and it's not that easy if you not that complicated if you follow just the patterns. But if you want to make it generic, this is complicated stuff. Okay, I'm out of time now. Thank you for your patience, and yeah, come to our booth, talk with me, or in the evenings with the beer. I can be bribed to talk with you and talk about internals on Xtext with the beer. So thank you very much. And don't forget to vote.